compare the first part of the book, Deal 71st. Actually, the book was really light. It doesn't have that much context to fill up 40 minutes, but I just add some much more details in it. So, and I also have some problems like questions. So the book also about how do you make our own neural network. But the first part started with the basic steps. Actually, what I also learned from this semester is that computer is stupid, but it's really fast. And we are smart, but we are very slow in calculation of those steps. So computers are really good at just calculating numbers and the frequencies of it, but we are much more smarter on the pre-processing or the processing in something like images or those kind of other subjective stuff. So before I guess 1970, there was also in the 80s, 90s. There was not that much computing power to do these kind of neural network steps. So at that moment, they had these concepts before, but there was not that much computing power. So these were just going to be ignored at that moment. But after the computing power increased, according to the book, people got much more interested to deal with these steps. So we are having enough computing power to do these steps, and also we are smart enough to code these steps. But we know that it's very hard to code, and Michael and everyone will know that we have to be very precise to make the algorithm, to make the computer to work as it. So we were just learning about those basic steps. Yeah. So the first part of this book is talking about simple predictions and simple predicting model. So human, when they have a question, they think and they want to find the answer of it. And also the guessing, something estimating or anticipating guessing process will be the same. People will just think about it and guess it and get the answer. They'll just think the question, the answer. So how about the computer? Computer will be a little different, the machines. They would have some inputs, which could be training data or some kind of other data which they have been obtained. And they would just process or calculate it and get the output. During this process, the problem is that how do we deal with the error? This is all predicting models or guessing steps. So there will be errors in it. At the simple predicting machine, iterative predictor of this model, the basic step is to minimize the error. So when we minimize the error, then the algorithm and the process will break and then just pull out the output of it. So we will just talk about how do we minimize the error. It's very simple. This is the truth example, which is the true data. So the second part of the truth example says that 100 kilometers could be transferred to 62.137 miles. So this could be the transformation kind of rate for it. But the first moment, we will not say that we couldn't get the exact transfer measure. So we just guess it. We just guess at 0.5. Then our error rate will be kind of 12.137, and the error rate could be a little large when you just think about that. So we higher transfer measures, so to 60. Then we will get 2.137 error terms. So it gets smaller. But however, the error term, the amount of the error gets smaller. So we just change the measure a little bit smaller. Then we could get the error terms which were smaller. So when the error term is minimized, and in the minimization, when we solve that minimization problem, we will get the exact number of these transformation. It's not very easy, but actually it'll take us more than 15 or 20 minutes. I did that too. We could take 2 hours to code these steps. So we have to think about how we could code these steps in some kind of measures. Then the computer would just do this multiple process every time to get that number very easily. So the next step is about classifying. Classifying, it is almost the same, but here they are. I think that classifying is just the top, like the big title of this part. But I think that the most important part is like error adjustment. They want to deal with the error adjustment, the automatic error adjustments. So like if we would just put the input in some kind of machine, and it'll like just do some calculation and pull out the error. Then with that error, we can just adjust our like slope or classifier, and then get an adjusted model, and just get a better result from it. So I think that was really cool. So I just want to introduce the process here. So at here in the first figure here, we can just easily see that there are two different groups here, the red one and the green one. So when a human just like see that picture, they could just easily like draw a line between them. How about computers? Computers, they need some algorithm to deal with this problem. So let's just say that this is the training data for this classifying bugs. So we just say that this is what's this? Caterpillar, and this is ladybug. Ladybug. So we just only got 1 point of those, 1 point of caterpillar and 1 point of ladybug here. And the problem is that when this is a unknown bug, how do we just classify it? A human just could say that, oh, this like belongs to here. So we could just say that this is a caterpillar. Well, how about a computer? How would they do that? So at the first moment, just like we just guessed, like it could be like 0.25, the slope of the classifier, 0.25. But we know that it is lower than the ladybug training data here. So we know that this is not a good classifier. So like we want the computer to adjust this problem here. So at the first time, we set the targeted value. So targeted value has to be higher than 1. Absolutely, to be a classifier. It should not have to be 1. It could not be 1, because when we draw a line at which like past 1, then it's not a classifier. It's just like dividing the this point here. Actually, then it's not a classifier. So we just make it a little bit higher, and we set it 1.1. 1.1 will be our targeted value here. But actually, the output using this equation, which we set as a classifier, it will be 0.75. Then the error will be 0.35. And but the best part here is that we can make equations which is related to this error term and also the slope, and we can just adjust the slope to make a better classifier. Just know that we just got an error which is 0.35 here. Okay, so we got a 0.35 error, but according to the equation, t was our targeted value. So targeted value means that we set some kind of different delta a here, the slope, and get a some kind of different number which is higher than the actual number, which is 1. So we got 1.1, adding delta a multiplied by x. So the error total could be defined as t minus y, where t is the targeted value, which I said before, and y is the actual output there, using the equation. This is not 1. Y is not 1. Y is like 0.75, which is from the output equation. So this was 0.35 before from our previous example. So when you just like disassemble this equation, then we can just get a plus delta a multiplied by x, which is the targeted value, minus ax. Ax was the output. So when we just get deducted with ax here, then we could easily get that error term is delta A multiplied by X. From this equation, delta A is equal to error divided by X. So the best part here is that we know X. X was, I think it was 3. X was 3 from our training data. And error term was 0.35. So when we divide 0.35 by 3, we could get how much we should have to adjust the slope here, which is delta A. I think that it was like 113? Yeah, it's 113. So we adjust the delta A, we just set the delta A as 0.113, added from our initial A, which was 0.25. That was our initial classifier, which was below the ladybug spot. So what we do is that from this graph, before that it was 0.25, but we add 0.113 from this slope, so it will increase a little bit. You got my point? Yeah. Then what happens is that that point will pass 3.1.1, which was our initial target value, 1.1. Exactly, that would pass that part. So we know how much we have to adjust to get that targeted value. So here, this is going to summary. We get the initial classifier here, which was y equals 0.25x, and then we refine it. And the refined value is 0.3667 by adding that the slope here. And also we can do the same thing with the caterpillar here. Just kind of reverse process. Not a reverse, a little bit different. So and here we just point 1.1 as a target value. But here, to classify between caterpillar and ladybug, we have to lower a bit to get the classifier. So it's not going to be 3, it's going to be 2.9 to be a classifier line. So our target value will change to 2.9. So we adjust it and do the same process and get this refinement at the classifier here. But the important part is that when we just use this simple process, we're just using the last training data example. And just say that we just said 1.1, or we just said 2.9. Then it's just gonna cross that 1.1 or 2.9, and that'll be our final refinement. But that is just using the last training data. So what we do is we introduce here the learning rate, which is the moderating factor. It's very simple concept here. So our initial delta A was just error divided by x. Yeah.
So when I was reading this part, I didn't get how he just get to the last line all of a sudden. Because it kind of reminds me of ordinary least square. We could actually this what he said is more like a simple way. We would have something sort of in the middle of the two clusters rather than two extreme closer to the left.
Yeah. You're right.
So I mean, it's suboptimal if you use ordinary square, but it's still not as bad as cube square. Right? So that's not the point of this argument here, but it's also
because you are human, you are smart. But the computer is not that smart. I also thought that when you just see this part, the best optimal classifier will be just in the middle here. Yeah, just getting the median, just median or mean from it, just crossing the middle here. But the problem is that these two are just a part of the data. We don't know how these subs will be grouped into data here, and also how would they group here, and the computer itself they just point out the data here, they just add a refinement, and then that they use some of the data and get a refinement that they group together. That was what I was understanding here. But like, if you just say that, if you just can draw like middle line there, then it could be easy. But we are not sure. Like, there could be other data there. So that is what the actually the learning factor and moderating factor does. Like, they wanted to just use like they just wanted to mitigate the what's that? Find a refinement and get something like a middle point in it. They just also want to use like other data in it. They say that they could mitigate that limitations by mitigating the moderating factor.
So if a computer does this, it will always be more vertical line than the always be the result.
That is why now we're going to talk about the learning rate. Yeah, before that they use the
Yeah, they say that it just moderates and mitigates the limitations, but I also think that you're right. But like they couldn't just like draw like the middle line there because like, it's all like mental process. Like, they also want to estimate data. I was just also
I think now I can mention the number here. Just something that mentioned is if it starts early instead of like the kind of vertical one, then because this is only the training data, so there's always room for the learning parameter to improve. That's why I did stop early. They will always have the tendency to go up.
not that like yeah, there could be a lot of like different steps, but if you use like software vector machines, then you'll like definitely get the middle line there. Like two different like stages, classifications. But the simple process is about like part of it, improve the process. Like, at one point, get a line there, and then also get a lot of data and get a line there. I think that this process is introducing the steps. But there's also be like multiple ways to classify the steps.
Yeah, I couldn't hear what your question was, but were you saying that this is really simple? Why don't we just use regular linear regression to classify? Is that what
Oh, actually, he was saying that it'll be optimal when you just like draw the middle line here.
Well, yeah, I mean, you have to discover what the middle line is, right?
But for this, it has the tendency to be closer to the competitor cluster rather than to the latent
Why?
cluster. I think that's the way he described it. Like you have this tendency, this classifier, this linear classifier will be like moving towards the other classifier.
You move towards the most recent classification, but if you had a training set of 15 data points and you like randomize their order, it's going to move back and forth with the learning rate, and so it's going to push between all the points. So this is a really, really simplified example using only 2 points. So obviously each one's going to have a very strong impact. If you were to do the learning rate example, start with the first point and move down, I don't think you would find the same exact line. If you were to start with 2.9 example, guess from there, and whatever your initial guess is also going to affect it because your learning rate is going to change. So there's all these other factors that go into even a simple example. If you think about it, if my guess is 0.1 times x is my first guess, my learning rate's half. I'm still trying to get to 1.1. I'm only going to move a lot farther from my line's going to be a lot lower slope at the bottom when I make my first adjustment. Then when I adjust to the second point, I'm not going to be at 1.6 or whatever it is. I'm going to be closer to like 1 change or 4.2 or so. It's going to be a lot lower slope because that initial guess affects it. So you can run this multiple times maybe with different guesses and different learning rates. And if you wanted to, in this even a simple example, you can aggregate all of those slopes. I mean, that's just a little bit to do it, but it's only 2 points.
Yeah, so when the point gets closer, you can also count for if they are like different different positions there, and it could just mess up. However, this process has just one incremental like adjustments in it, so you could just get the precise classifier.
Yeah, I mean, okay, so the point of this slide is you don't use learning rate, and you just keep moving the line to your most recent training example.
Yeah.
With learning rate, you're taking into account your previous training examples, right?
Yeah.
All right, so let's move on.
Okay. So here you can just set the learning rate. Our book is 0.5, but you can set it by your own decisions in it. So you can just set the number, just multiply it, and then after, whatever you do refinement would get a little bit like a mitigated and also like moderated function, and also there are some machines that get that result. So the next part is that actually this part title is not Boolean logic function. It's about like multiple like separator, multiple classifier. I also wanted to learn about like Boolean logical functions. So I just like titled that Boolean logic function here. So first, like the Boolean logic functions, it means that there are binary kind of like inputs in there, which could be 1 or 0. And when there is like, it could be just defined as like AND OR function or XOR. And means that if they both have like true true results in it, then we just can get that it is true. The output will be 1. And then OR means that if like one out of like those two like out inputs are true, then we can just say that the output is true, 1. And XOR means that one could be XOR means that like, they could be OR functions, but it could not be in the both like both same functions. So like XOR will be a little bit different here, and XOR will be the special like kind of like case for this part. So first of all, when logical AND says here, we can classify 1.1 here by using a simple dividing line. And it could be just divided by this green line. And it could be just divided by 1 classifier. But logical OR, logical OR, it could also be divided by 1 classifier. I'm very afraid to use but and however because like Abby was teasing on me. I use a lot of like but and however, so be careful with that. So dividing line will be just like simple classifier here, which is also not a multiple classifier. The problem comes up with XOR here. By the definition of XOR, 0, 1 and 0, 1, 0, here they are both true, but 0.0 and 1.1 they are false here. So they wanted to classify between these. So like, could they classify with a single like one line or a single like classifier? So they could not do that. The solution was like so simple. Like I was like so surprised. Like, so they just say that we use multiple lines, 2 different lines here. So we classify this and this. But one thing I was curious about was that if they want to classify like this, they have to set this part and this part to be in the same area, like the same domain, like the same kind of like a classified area. And they have to set this part as a other separated area. One thing I was curious about, is this 3 all different, or these 2 is the same area, domain area, and this is in the other divided area. So
I think there are only 2 areas.
So this one and this one. False area. So that only that true area.
And you count false in true. Like it's true. Okay.
So when you quote it, you just say that this part and this part is the same domain area, and like just bundle it.
I think so. That's what I understand.
And then this is the other area here. I just added this part like this morning. I was just talking with Michael, and during that conversation, I just added this slide. Now we're just talking about Neuron. We're just trying to build a real artificial intelligence here. So the simple way to talk about a neuron is that it's kind of like the basic one will be a step function. step function here. So they just use a dial here. Means that if the input does not reach the threshold, then the output would not come out. However, if the input somehow signals or makes something like when the input fires the threshold, and then after it'll just pull out the output there. So that was the step function. As you can see here, there is a simple step function here. So here there is no output here, and the threshold will be this moment. And when we get over this threshold, then after this function gets this activation function gets fired. So this was like the basic concept of the step function.
Sorry. Well, so that's like a neuron fires. It passes along the information.
Yeah.
The threshold is met.
Yeah. This is kind of simple. So, but the problem which I was talking with Michael today was that how about a sigmoid function? Like my idea was that sigmoid function, does it fire?
Yeah, it fires.
Does it fire?
It's more gradual. Yeah.
It's gradual, but it fires.
Yeah, it fires.
But
it
then-
passes on along information.
Does it have a threshold?
No, I mean it's continuous. It's a continuous function instead of like this type.
Continuous function.
It's supposed to be more like nature. Like I don't know, maybe neurons fire a little bit.
That was kind of our discussion, is that there's got to be some processes. Like the example I think we were talking about, like waking up in the morning, where like light comes in through your window, and if there's a little bit of light, that's not going to start totally trying to wake you up. If there's like more light, you might stir you, but you need a certain amount before your brain is actually going to go like, all right, we have to get up now. And so there's functions in your brain that will fire automatically, and there's some functions that will, at a certain point, maybe fire a little bit of the chemicals that wake you up, but not all, not a high enough dose to then activate the next neuron. So you might get a little bit of the process before the path won't complete, because as we'll see later, as the weights maybe later down the path are strong enough that you lock to overcome. So as you go through, so there might be some where it's very steep, and some where it almost looks like a step function, but the sigmoid function is just much steeper, and some where it's much more gradual depending on the influence.
I think that Fang will know that answer. But
These activation functions can be. There's a lot of different activation functions. I don't know. In this book they just showed the sigmoid function. There's the regular linear function would be whatever's the input is also the output. There's no transformation. Then there's ones where if the input is less than 0, then the output's always 0. Once it reaches anything greater than 0, then the output is the input. That's the rectified linear unit. Then there's the tangential.
Yes, they have ReLU, they have soft plus.
Yeah, soft plus is like a type of sigmoid function from. What is that one from?
So
Soft plus.
your sigmoid is like you write it here, like this, right?
From 0 to
Then
1.
your soft ReLU would be something like this,
That's
and
right.
it hits 0, it goes like this.
Yeah.
ReLU. And you have soft plus ReLU. ReLU. This is like you can use this later when we build our neural network. And then we have soft plus, which is almost like this.
Do you know TANH?
I saw the name, but I didn't remember.
It's like the sigmoid, but it crosses through the
1 to
0,
minus 1.
and it goes from -1 to 1.
Oh, so like this?
Yep.
Yeah.
Okay.
And there's even more.
Yeah.
But the sigmoid function is very common, especially for a classifier, binary classifier.
It's come from logistic regression.
Yeah. It's the same as
That's why it's so
logistic regression.
famous. The sigmoid function is the same as logistic regression. So that's why it was widely used.
It's also because they have like because if they have the boundary like between
Yeah, no, because if you take a function and create a derivative of that function, it creates a sigmoid function. So you have a function of x, you just create the derivative to make a logistical regression, it creates a sigmoid function. That's why they use sigmoid.
Yeah. So I was also like thinking about why like sigmoid functions. Like the book say that they wanted to replicate like human like brain process and those like neuron process. So what I thought was that if we have like multiple like billions of like binary kind of like step functions, then it'll look like sigmoid function. Like as Michael just said, waking up in the morning. Like 70% of our like step function would say that you have to wake up, but 30% would say that I'm not still wake up. So like it could make some like sigmoid function. I thought so like that, but like we were not sure about that. Like how we could just define it.
Very different.
Yeah.
I think it also depends on different situations, right? So if you are waking up in the morning, then you say that's a threshold. But if you are tasting like sugars, then a little bit sugar will give you this sweetness. A lot of sugar will give you a lot of sweetness. Just
That was like my whole.
Yeah, so there's a bunch of examples, right?
Yeah.
So it also depends on all these circumstances. And
Yeah.
trying to measure that also then determines all the other factors around it.
So here, they use the matrix multiplications here. So they use the input, and they use the weight in it, and they use the matrix multiplication calculations. So they get the output by using the matrix multiplications, and using also the sigmoid threshold function to get the output for each part of here, outputs. So they use the sigmoid functions, threshold functions, and also the matrix multiplications to get that function to be calculated. I think that we all like deal with this part. So yeah, and it says that we can also use the 3-layer, and the second layer will be a hidden layer, which is named just because it is hidden there. It doesn't have any kind of special meanings there, as the book says. So we can also use multiple matrix multiplications, and here they have the output hidden, x output. The same process using the matrix multiplication, just like increasing the dimension of the matrix. I think that we all have to deal with this part. This is the end of the part 1, and the second part will be about the error adjustment of the matrix multiplications. Thank you.
Here, these neural network processes to the line graphs, or the differentiating between ladybug and multi-category. So far, we have just draw a line between them, and we'll have to adjust our line if there is an error that we considered ladybug as a caterpillar or vice versa. So second part is how to assign the errors to the weights, and how you update your weights depending on the errors you get from the process. So this is the second part. So you get a, let's say, output error, right, from the simple network, I think, and you have an amount of your error, and you have a weight. So there are several ways to assign these to the weights, and the key players in this system, I would say, are the weights, because your inputs always change, and your weights should not change. They should stay constant and should work for the majority part of your calculations, so whatever inputs you use. Okay, now first way authors suggest is to equally split the errors to the weights. Say, okay, I'm going to split half to the first weight, half to the second. I think your terminology is confusing me a little. Where is the error being assigned to?
Error is assigned to the weights. Think of these twin nodes.
So the error is assigned to the preceding node. So how much error? So there's an error in the output, right?
Yes,
on
yes.
the right side. So how much of that error comes from number 1 on the left? How much of the error comes from number 2, 1? So,
Yes.
so how do we assign error to each of those nodes?
Nodes.
Like this says one way is to just divide it in half.
Yes, and this side equal. And this the problem with this is the node 1 is the contributing in the first layer. Let's say that node 1 is contributing 3 times more than what's getting at the input, and the node 2 is passing it through as it is. And one solution would be, simple solution is normalizing this error assigning. So you normalize based on their weights of their and and another name is backpropagation, right? That's backpropagation. So what it looks like is that you have different links to the nodes in between them. So you should do this for each node of the layer separately, and we're going to combine the whatever comes to these node. Let's say these 2 lines comes to these nodes, so we're going to combine them. So we're going to multiply these to their corresponding errors and add them up. And one more reminder is an error was defined as the difference between your output and the actual value. What is the actual value? Okay. So another problem we'll run into. We know what this output error is, so it's just the difference between our actual value and the prediction. But the thing is that we don't know what would be the error here, because if we assign the error to this node, then how we're going to compare to its actual value, how much we are missing by, let's say, up to here, up to this process. So there is no, this is a hidden layer, it doesn't provide actual results. So you're going to have all output here. So one way would be, as I said, to combine all the weights that's coming into these nodes, say this one and this one. And so you're going to multiply normalized weights to the errors of each output error and add them up.
So, yeah, go to the next slide. Yeah, go to the next slide. And then take time to explain how we get each number in the top one.
Okay, how we got these numbers?
Yeah, just I want you to walk us through splitting the error.
All right.
For each node.
So well, these are the errors of each. Let's say. Okay, this is the first step, right? This is three layer with the 2 nodes in each layer network, and the final error outputs are 1.5 and 1.5. So we're going to assign these by weights. So we have 2 weights coming in. One is a 2, and another one is 3. So we're going to proportionally assign this 1.5 to these two nodes. So we're going to assign 0.7 out of 1.5. Sorry, 0.6 out of 1.5 to the first node of the second layer, and we're going to assign 0.9 out of the 1.5 to the second node of the second layer. So
based on the weights.
Yeah, based on the weights, normalized weights. So we have all assigned now. We're going to do the same procedure here. Out of half, we're going to assign 0.1 to the first node and 0.4 to the second node. And we're going to
0.1. Why is it 0.1?
Because weights are 1 and 4. So if you normalize, it's going to be 1/5 and 4/5. So if you add these up, so 0.6 plus 0.1 would be 7. then 0.4 plus 0.9 would be 1.3. So you have an error assigned in total 0.7 to the first node and 0.3 to the second node. Sorry, 1.3. So out of so if you add these up, you're going to have 1.8 here and 1.8 here. So all 4 errors are assigned. So you're going to do the same thing to the second step.
And you just do the exact same thing. So
Right.
just to refresh my memory,
Okay.
where does that initial error come from? What do we, that error?
This?
No.
This?
Yeah, where does that even come from? What are we dealing with here?
Actually, this is between your difference between your prediction and your output. Sorry, actual result.
So what are we predicting? What?
The text does not provide what we are working with.
Well, not
Just-
exactly, but conceptually.
Conceptually.
So, I mean, basically, we've taken some training data.
Yes.
Right? And we know what the output should be from the training data, right?
Yes.
So, maybe it's a caterpillar, maybe it's a butterfly, maybe it's fraud, maybe it's not fraud. We know what the output should be.
Yes.
So we take we have some neural network, and we have some weights between some neurons. We have these layers. So what you need to understand is how does the neural network get built in the first place? So first you create these weights, and one way to do it, you just randomize the weights, right?
Mhm.
You learned this in the end of the book. You
Yes.
probably learned this. So you randomize the weights. Then you take your training data and you pass it through the network with some random weights, and you look at the output. And you see if it matches with what you expect. And it won't, because the weights are just randomized. So there's some error between what your training data says it should be and what the network said it was, right? So this is part of the training phase of the network. You get error every time you pass it into a training sample. And then we refine the weights. So the next time we put a training sample through, the error would be a little bit smaller. Right? And then we refine the weights again. So in the training part of the neural network, we're always updating the weights. And the weights are like the book says, the magic, I don't know if it says magic, but that's what makes a neural network special is, and work really well, is we refined all these weights, and they help us eventually usually get the correct, pretty close to the actual output. And the error is minimized quite a bit. So that's kind of what we're doing here. We're training the network, teaching the network. When you actually use the neural network, it's already trained, and you take you're not training it anymore. You're using it to classify or predict. Then you're taking items you've never seen before, you pass it through your network, and you look at the output, and those are your predictions, right? That's what you predict. You're not updating it again. You're just looking at the output. But in the training phase, we're constantly updating the weights. So go ahead and keep going.
But this is just the one step of updating the weights. It requires several calculations. We can simplify these to the calculus of matrix. This is actually solution for our previous problem that we solved, and this part is a little bit bigger or complex. So if we didn't have this normalizing, it would be as simple as the transpose matrix. So we just weight of the matrix plus this diagonal inverse, and our error for the hidden layer would be this transpose matrix of the weights multiplied by the error output.
Yeah, and go back So I said the magic was updating the weights. We haven't done that part yet, right? We've only identified the errors associated with each node, which will help us update the weights later on. So, go ahead.
Okay.
Continue.
So this slide just explains that we can apply matrix to updating the weight. So this is actually output formula, I think. This is what the sigmoid or the logistics expression. So what you are actually doing here is you're multiplying your inputs to the weight, and you are summing it through all the weights. And this is a sigmoid function. You are doing the same for the second layer and same for the third time for the third layer. And this is your output for the K node. The K node. The question is, why don't we use just the fancy algebra to work from this calculation? And the tax says it would take a tremendous amount of time to calculate. Or let's say if you had 500 nodes in each layer, it would take like even if you had 1,000 weights between -1 and +1, I think I missed the minus here, sorry. So in total you would need 16,000 years for 1,000 training. So then we can use analogy here to solve our problem. So you are with a torch in somewhere in the hills, and you want to go to the lowest bottom of that place. So what you would do is that you would look for the lower ground than you are staying at. So by that you will, if you go down, you will eventually end up at the lower place. So we could use the same thing in this network error problem. So if it's a complex function, I think everyone knows you just take the derivative of that function and make it equal to 0. But here text goes into more details and a simple explanation. So if you have a U-type function, it considers this parabolic function as an error function. And let's say your first training result gave this much error. So you want to minimize it and so decrease your weights. And if you did overshoot, then probably you should decrease your weight. Right? And here you need to increase it. So eventually what you want to do is you want to end up in this bottom part of the function, error function. So and another problem would be when you will get closer and closer, if you take equal steps, you may, like I said, overshoot and pass over it. So you want to take smaller steps when you get closer to it. So this is just one function with one independent variable. If you have more than one independent variable, this is a function with two independent variables. Here the function output looks like terms, or how do you call terms? And you want to end up in the bottom of the valley, and it should be a deepest valley, not any valley. So what would be like ending up in a wrong valley? So if your function have several critical points, you may end up in here, right? And you don't pass through this. And here, when you supply extra values, your error is going up, not down. You may stop training it before you actually go to your optimal error point. So another question would be how you would measure the error. The first option is just take the difference between target value and actual value. But this has some disadvantage, as when you sum your errors, negative and positive errors may cancel each other out. And you could also use the absolute value of target minus actual, but as the text says, slope isn't continuous near the median, so you should take smaller steps. One thing I didn't understand is how this would help the smaller gradient approach to the function. So if you have any idea.
Which one? What's your question?
So how this is better than this?
That has a kink. So second was a kink.
Oh.
But the third one is continuous.
Oh, continuous. Okay.
So we can get the derivatives from the kink one.
Right. Okay, so then they list several advantages of using a squared error method. So next question is, how sensitive is the errors is changed to the link weights? So this is the main slope of the error function at the given point. So what you want to do is, I think you want to achieve this slope to be 0 when it becomes, let's say, a horizontal line. And it goes through several calculations. First, as we chose the square error method, then you gotta take the derivative of it. Then
you can go back to the previous slide. So you see that derivative.
Yep.
How do you read that? How does that read?
Okay.
Intuitively.
All right. I'm gonna try that. I'm not going to be perfect. So this is an error from a node that received errors through the weights of j and k. Is that right?
I think that's how much error changes when we change the weight of each one.
Yeah.
Change.
What'd you say, Aaron?
How much the error changes when you change the weight for JK, something index there.
Yeah, how much does the error change as the linked weights change? That's all. So if you look at that top left one, you see this very steep slope. That means the error changes a lot with this, as the linked weights change. So, like you said, once it's horizontal, then the error doesn't change, right? As the linked weights change. And when the error changes a lot, you might make a little bit bigger. It'll minimize the error more with a small change.
Okay, so our function is based on the sigmoid function, derivative function, and they take derivative as this is a complex function. They split into they call it inner function and outer function, take the derivatives, and here they we ignore 2 because we just care about direction. And finally, the final output is this. And you can call first part as an error, and the middle part is a function of the sigmoid function, complex function. So you're just multiplying the sigmoid function to itself with the difference between 1 and lastly output of that the hidden node. So we have this function now. So you have this result. This is your old collection of old weights, and this is your assignment to the how much you want to change your weight.
Your learning rate?
Yeah. And then you're going to end up with your new value for your weight. And you can apply the matrix calculation to this as well. So they're going to take an example of what we had previously and calculates through this function we achieved. And they found that at the learning rate of 0.1, change would be 0.006. So we had the I didn't understand is what this number is corresponding to, like which node, which layer.
Here you are doing the multiplication weight between hidden and output layer. So the 2.006 is the updated weight for the output.
So to this weight, right? So you're gonna change this by increase it by 0.006. Last part, it talks about preparing data. Some problem in your inputs would be when you choose very large values, then your sigmoid function gets really flat, and you're gonna lose the advantage of what we call gradient advantage. And with your outputs, you could also choose it to be between 0 and 1, and outside of your region would be anything below 0 and more than 1. And with randomly choosing your initial weights, mathematically it's advised to choose the weights depending on your the weight links coming to this single node. If you have, let's say, three weights coming in, you should choose the initial weight as somewhere at 1 divided by square root of 3. If it's 100, 1 divided by square root of 100. And another problem is if you choose your weights to be 0, then you would be eliminating the input signals that are coming to that node through that link. and that's it. And next week we're gonna apply these to the Python code.
You have and other stuff. The constant here means once you assign the number in there, it will not change. So when you are running the TensorFlow, this number here will not change. However, later you will see a placeholder where you can put in your variables, and that part will change as the neural network goes on. So we can try a simple function called result equals to tf dot multiply x1 and x2. And then we can print the result here. So if you run this, the print result here, what you will see is it will give you this one, the tensor, and have some attributes later here. So in TensorFlow, when we write result equals to this one, this is not activated, meaning the calculation in here is not made. It's just stored like a function saying this means the tensor with these attributes. Then to actually make this calculation happening, we need this step. So with tf.sessions as ses, output equals to ses.run this result, this function here. So run this and print output.
So just multiply.
What?
It's not just multiplication.
Yeah, it's not metric multiplication. It's you see, it's just one. The first one times first one, second one times second one, and give you the result. So basically, this example here is tell you that once you define what is the calculation in TensorFlow, what you need to run it. And the way to run it is, well, I write this with function here. So basically the way they run it is ses equals to tf dot session, and then ses dot run your function here. And then you need to use ses dot close. So in this way, you start this TensorFlow and do your calculation, and you need to close that. However, to just write it short, you can write like this. So we can. Okay, so that's it. You know how to use TensorFlow. No, I'm just joking. So just to give you a more like intuitive example how to use this one, I was doing something from the an online example they posted online. So this example is to use neural network to identify the traffic signs in Belgium. And what they use is the data set here, the Belgium training and Belgium testing. I'll post everything on the class folder, so if any of you is interested in replicating this process, you can definitely use that. Okay. So just let me.
These are traffic signs?
Traffic signs. So. Like this. Traffic signs. So first, what we define is a load data function. This has nothing to do with the neural network. It's just a way we load data from our file. And if you can see here, we have one called label, one list called label, one list called image, is we are going to use this list to install all the to store all the labels and images to store all these images. And then we are just going to define where the root path is. So I'm going to put all the training and testing folder under this traffic folder, and I define these directions is equals to this root path plus this training, and this root path join this testing. And I use this load data function to load all the training data. Then I transfer it to NumPy arrays because if you think of images, we cannot read it directly through for machines. How machine read that is read it like a list of pixels. So for us to use a scikit image pack library, which I use here, sk image, they only work with NumPy array better. So that's why I transfer them to NumPy array. Actually, the long list that you'll see in the following would be the how do we clean our data and how do we make our data ready for use for this neural network. Because if you are trying to do any machine learning, I think you will spend at least half your time cleaning your data, right?
Yes. A lot of preprocessing data,
Yeah.
So in its current form, though, it says images equals NumPy array. I mean, there's still images at that point.
Yes.
You haven't transformed them into pixels yet.
Not yet. But if we can, if we see how do we, actually I already have some of here. When I read the images, it will read from its pixel format. But let's just see here. So I print the images dimension, the size. So we can see it's called one dimension. No. So the size is 4,575. And if we look at image number 1 or number 0, it gives you this list of pixels. And then I print out the labels.
That's an RGB for each individual pixel.
Yes, RGB pixels. If I print out the labels, it will give you a distribution of each. So the number one traffic sign appears this much time. Number 23 appears 350, more than that. So we can see our data set is not like a normal. It's not a uniform like data set. So they have different appearance, different.
Maybe that tall one is a stop sign.
Yes. So we are definitely going to look into that.
So what is the y-axis means?
The frequency.
Frequency of RGB pixels?
The frequency of this is the label table. So this means if you think of label that's in our training data, it will tell you. So in this picture, we have the stop sign appearing. So stop sign, let's say if the stop sign's label is number 23, and it appears more than 350 times in your training data.
So there's basically like 61 different types of signs, right?
Yeah, 62. Yeah.
Oh, 62.
Yeah, it's almost there. So in the next one, we just do some visualizations with matplotlib. So this one is a random function, so I just use this to random pick 4 images to see what it looks like. It will output the shape. It will output the shape here and the minimum and maximum.
Minimum R or G or T?
Probably. I'm not sure because when I read through this code, I'm not sure what they are doing with this minimum and maximum. But here is the here is a shape of that. So
why is it 3 dimensional?
Because we have 3 colors.
RGB. right? 3 colors.
And that's the average R, G, and B.
No, it's for this specific. So this RGB here over this specific sign is this much.
Yeah, you have 108 pixels in height, 74 pixels in width, in 3 layers for 3 colors. That's why three-dimensional array. That's why we will have the 3, because we have 3 colors.
Yeah.
And min maximum because RGB is between 0 and 255.
Yeah.
For example, in R, in red, if you get 0, you have no red in that pixel. If you have 255, you have a full red in that pixel.
I see.
And you can have a range between of them.
Yes.
So even though the signs are different shapes, the number of pixels high and wide are for the entire picture.
For entire picture.
This is the point.
So in the calculations of the red, green, and blue, it's going to include the background portion as well?
Yeah. It's for the full image.
Go down. So each shape should have the same dimensions. No.
No.
The other thing is that if you train them on larger images, like if there was more space on the side, it's going to be harder to be accurate unless all
Yeah,
the
so
background
that's why
images
we are going to process this stuff. So I just give, yes.
You have to normalize image size?
Yes.
Okay.
So here I just plot all this image size with, this
Sorry,
is,
one more question.
yeah.
Can you please go back? Although Mauricio explained, but we don't really understand what does the element in the shape means. We have 3, right?
Height, weight, and depth.
Or height with depth.
Yeah, 3 dimensions. Yeah.
Oh, why is 55, 53, 3?
Yeah, 55 height, 53 the weight, and 3 depth. Because you have 3 depth because of 3 colors.
Yes.
If you are, huh?
Shape of what?
So this shape is
Of
here,
the
right?
how you represent the, because all this picture it's you are importing has a matrix. Okay, it's a number representation. It's in a matrix. It's a 3-dimensional matrix. So you
each axis you mean means red,
What?
green, blue, right? That's what.
yeah no yeah you have the height and height the image
See, this one
is the height. 122 is the
width.
width,
Yeah.
and 3 is the
3
depth of the image. You have because you have 3 colors.
3 colors.
3 colors.
Yeah,
Green
if
and
it was
blue.
grayscale, it will be just 1.
But the second one is not 4 times like higher than the other.
Yeah,
Is it higher?
but you see, all then is 3.
Always 3.
Always 3 because you have RGB.
It's
Okay.
3 colors.
But yeah, what Ian say, because all image has different shapes. You have to normalize this one to the
Yes,
same.
normalize it.
Yeah,
We can normalize
Min and
it
max.
so we can have the same number of input.
yeah, because RGB the minimum 0 and the max is 255. 255.
So it's
Yeah.
RGB's minimum and maximum.
Yeah.
Okay.
So if the minimum is 15, that means that RGB, the lowest, whatever RGB is 15.
Yeah, 255.
15.
If you, for example, if you have a square, just red,
Yeah.
the RGB will be 255
Yeah.
for R,
Yeah.
0 for green, and 0 for blue.
So zero. Oh, so.
If you are just red, and that's why the representation of each pixel will be represented like
If
this
all
one.
255, it's white. And if
All-
all 0, it's black.
Yeah.
Okay, so then I plot, here just plot one by one, so just see what our testing data looks like. So if you see here, this level 3 appears 15 times, so if we just identify the what is most frequently appear, we can see in Belgium, in this country, they actually, here, they actually have the no right turn 285 times. Let me see.
Level 32.
Oh, it's above.
Above here.
Above. So, yes, so the bicycle stuff. the bicycle stuff appears 285 times in the training data set. Yes.
Can you scroll to the top row again, please? So there, label 5 and label 6. To me, that looks like the same sign, just from 2 different angles.
Could be.
Let me see that.
But this is training data, so someone
Yes, so
manually
that-
coded, right?
Yes. It's manually coded with this training data, but I'm not sure. But why do they do this?
This is called real data.
Okay.
Okay? It's always like that.
So you can see you have different.
Oh, the parking too, right?
This parking.
Very similar. No, it's different.
Yeah, parking for the handicap, parking for the parking of cars. So because you see we have all this training data in different shapes, right? We need to uniform them, so we need to transfer them to image size of 28 by 28. So what we do here is we use the scikit image transform resize function to transform all the image to 28 by 28. So that's how we compare them.
Does it upscale too?
Is there any leaking you choose 20 by 20?
Well, it's provided by this tutorial. I think the 28 by 28. I think most of them will compress it, so they don't need to generate random stuff. I think 28 by 28 maybe the
smaller is
smallest.
better for more efficient,
Smallest.
more efficient networking.
Yeah.
So when you're compressing them, you're still getting the same image compressed. You're not cutting out anything.
Yeah, you'll see the output of this compression.
I mean, you're losing pixels, right?
Yes.
You're losing a ton of data.
And also we use this RGB to gray. So we'll transform all the colors into grayscale. We'll transfer all the colors into a grayscale using this RGB to gray library, because when you identify traffic size, in this data set, especially this, the color doesn't matter much. So if you use here, when I'm running on the spider, it works. But if I run this on the Jupyter notebook, it still gives me a color there. But it does not affect our result. Just let me see if I can.
It still says it's 3 dimensional. It should be 1 dimensional.
Yeah, it should be 1 dimension. Maybe there is some mistake in the code.
Well, isn't grayscale just still being represented by what
You can make it.
Oh, I see. I do this after.
Oh yeah.
Yeah, I do this after.
Hey, rerun it. Can you rerun it?
I should put this in the previous one, then run it. Because here,
Can you rerun that so we see the grayscale?
yes. So I need to put these 2 lines in above, right?
I think so.
Yeah.
But one thing is that I'm transferring this image trans into NumPy array. So I'm not sure whether all my plotting code will work.
Okay.
Let's just run it.
I have to run since the beginning, right?
Oh, I see. I need to
So
run everything.
everything above it first. Whoops. I have a question. Do you guys take Professor Gogan's machine learning class?
Next.
I wonder
variable, now the shape changed to 28, 28.
Yeah, and
There's
this
no,
one.
there's no the third RGB here. They are just gray, but it seems to me like a little bit warm, like with orange stuff. I don't know, maybe that's the collaboration of my computer's color setting. Probably, but now it should be gray. Okay. Because it's only use white and black to demonstrate that.
We know.
Okay, yeah.
If you change to that, then the max and min is between 0 and 1.
Oh, that's the percentage of black or white. Must be one of them, right? If you. And now, after we do all this cleaning stuff, then we go into this TensorFlow code here. So like I previously said, we need a placeholder first. So to contain this, to contain the stuff that will change. Now what we do here is d type equals to tf.float 32. That means we need a float, but I'm not sure why they use 32 here. And I was doing some research on that on Google search, and they say the tf.float 32 or 64 equals to NumPy's float 64, or no, because NumPy's float 64 equals to Python's float, and this is based on NumPy, so they need to use these legacy settings like this one, float 32, to make this running.
And this is going to be, this is like the C# and the C, the old C and C++. This
Okay.
is default data type. So
Oh,
I think that's why they're using INT32 and float 32.
yeah, because when I search online, now in Python you just type float, and you give if you want a unit to be a float, you just tell it to be float. But here, because this is built on NumPy, and NumPy have this legacy settings like float. If in Python's float, if you use NumPy to make give definition to that, it will be float 64. So that's how they make this like professional set, maybe the C++ stuff. But anyway, so we have our x and y, the TensorFlow placeholder. Then we need to create our flattened data. So we'll flatten our input data to, I think the flatten only works for image, right?
We'll flatten data?
Yeah.
No, yeah, no. It's because your data is a matrix 28 by 28,
Yes.
right? What you're gonna create? You transpose your matrix 28 by 28 by 1 by 28 by plus 28 is how much is 28
Yes,
times 28? 700 and something like that, right?
No.
760. Yeah, so you're creating a change for two-dimensional array for one-dimensional array. So you have
Oh, okay.
700
So
input
basically,
layers.
just like now
Yeah.
we have
Create
28 by 28.
a 4x4 matrix. For example, a 3x3, a matrix 3x3.
3x3.
Yeah. Okay. Okay. Right. So when you flatten this, you are creating 1 by 9.
Oh.
9 by 1. 9 by 1.
So
9
like
rows, 1 column. Yes. A, B, C, D, E. Yeah, perfect.
Those will be like the input neurons, right?
Yeah. So yeah, when you do this flatten, you will change your multi-dimensional array into one-dimensional array. And so we are using in business. We are using you get used to one-dimensional array. So one sample, one evidence is just one-dimensional, right? So when we are dealing with image, we are doing a multi-dimensional array.
Yes.
It's difficult for us to understand a little bit,
Right.
but it's just like this. This is one example. So when you flatten your image, you change from multidimensional array for 1.
Yes, I think I should not write like
Then-
a matrix.
Yeah, this
I
will
should
be
write like an array. So
yeah. So this will be
store
our
the
input
data like
layers.
this one. And then we have here, here,
Yeah, this is in array.
right? NumPy array, like this one. So we store the pixel or the picture data like this,
Yeah.
and we need to flatten it into 1 dimension.
Yeah.
So this will be here. Okay, thank you, Mauricio. And then we are going to define our layer. So the layer here is the way we define our layer. We give name like logics, and then TensorFlow.contrib.layers.fully connected, and we want to use the image flag in there, and the 62 means.
That's the output. Number output.
Yeah, it's you're creating a hiding layer with 62 neurons.
Okay. Oh yeah, because we have.
No, that's the output layer.
Yeah.
We have 62. Yes, 62 labels.
That's the size.
We have 62 labels,
Yeah.
so we need 62 outputs.
We're gonna create a hidden layer.
I don't have it. Okay.
And then this tf.nn.soft class is where you put our function. So like we previously said, we can write Sigmoid here, write ReLU here.
What?
The soft class is like a generalized logistic regression that lets you have.
Yeah, soft plus is we can try different things later, but here a ReLU is equals to 0, and once it passes to 0, it goes like this. And soft plus is more like this. This one is soft plus, and I'm using soft plus here because Vincent told me that he's using deep learning to predict fraud, and soft plus works best for his data set. So I try soft plus here, and we can try different methods later. The Sigmoid or the ReLU, we can see the different result. Then we're going to define our loss function. So the loss function, there's so the loss function here we have there's tons of different loss function here. We just use one in this reduced mean category, and they also have loss function based on so here we have the input of our labels, and we give our this is the true y. This is the label of the y. The largest equals to largest. Largest is here. So previously our layer. So this is our estimated stuff. Or the process. This is complicated, but I'm okay. So
So is the loss function the error function that
Yeah.
way? Okay.
it's called loss function, or it's called cost function. So it give you can give incentive when it makes correct guess, and you can give punishment if it gives you incorrect. So measures how long is your prediction away from the true value. And they have different loss functions here you can use in TensorFlow.
It's like the error function in book.
Yeah. I was actually searching for that, but I'm not sure whether they are the same.
Yeah, I thought the book was a little confusing. It calls it the error function, but I just interpreted that as the loss function.
Yeah, and so basically for the loss function, they have also meaning this is a cost function. So what is the cost to get the right stuff? And then we define an optimizer. The optimizer is what we learned in the algorithm for the gradient descent in the book. So just like you see in the book, so for the function like this, an arrow function, it says go down till go to this point here, right? So there's different ways to do this. And we are using the Adam optimizer here and give it a learning rate. So the learning rate is what you learn in the book, specifies how big steps I should take every time I get an error.
So how should we decide the learning rate?
Well, you can try different learning rates and see if that result improve. And I think there's if I play with this more, I will get a feeling of what the learning rate how really affect your result. Actually, I was previously doing the neural network to identify cat and dog, and if I adjust the learning rate, I set the learning rate to usually it will be equals to 1 to the scientific is the like this, right? This in this situation. And I think I try to modify this to minus to the 10 to the power of -6 or -1. And in that data set, it actually works best when it's -4, I guess. So we can you can fix the optimizer here and try different learning rate, or you can. I think for me for now, to my understanding, it's a try and error.
So there is no rule of thumb.
What?
So how do you look at alternative?
Well, that's a tricky question because if you see here, if you see here, this training has all these different, all different optimizer, like or even these. We have Adam optimizer. We have this optimizer. In this example, I didn't choose this because it's given by this the author.
See if you have SDG. SDG. Should be.
Try S. Go for stochastic.
Yeah.
Oh.
SD.
SE.
Or maybe it's just called gradient descent
Yeah. Region.
for G.
I believe it will be capital.
GT.
Can you say that again?
SDG. Yeah, it should be SDG.
SEG.
D.
Looking for stochastic gradient
Yeah, it's
descent.
stochastic gradient descent. Yeah. Yeah. G.
G.
Okay. Yeah.
SG.
The technique you are using for training in optimizer is stochastic gradient descent. This is the most famous one. Is the way I use it. And they have some variations. Adam, it's a very good one. It uses the same technique, stochastic gradient descent. Okay, but you have several ones. Huh? Yeah. Yeah. It's very difficult, even for math. Even for math, for mathematicians. The technique is that stochastic gradient descent. You have to train it several times to try to find the global minimum. It is very difficult. So they have the researchers propose several techniques, right? The main one is stochastic gradient descent. Nowadays, for TensorFlow, people are using Adam optimizer. They have some papers published about Adam. It's a very good one. They change the way, and they are using adaptive learning rate for doing that. It's very interesting, but it should be there. And one important thing about TensorFlow, you can define your own optimizer. You can create a function to do that. So for example, for my problem, Adam is not very good, but you can develop your own optimizer. You go into the math and write your own functions to do that. It's very difficult, but you can do that.
Adam optimizer is only like 2 years old.
Yeah, and it's very powerful.
Yeah, just give you a heads up for those of you who haven't taken the machine learning class yet. So we are talking about global optimization or local optimization is when you have something like this. So if you are using gradient descent and just see if this global. So our desired destination is right here, right? We want to reach this point. However, when we use gradient descent, it tells you to select a random point and perform that task. So if you select here or here, you'll finally end up going to here, right? And what they are saying, taking random point is you set your starting point differently. So you random select your starting point. So point here, or point here. So just try different times until maybe 10 times or 20 times until you just reach one of these. If you take this here, you will get this correct answer till this point, our design point. Yeah. However, if you just take just 1 time or 2 times, you will finally go to this local optimizer here.
Yeah. I found it's spelled gradient descent optimizer with capital G. Yeah. Gradient descent optimizer.
Okay.
Okay, so starting from random points is the same as setting your initial weights randomly, right?
Yeah.
So you have to create a new network every time.
Yeah. It's the process. It's algebra, right? It's random statistical. So you'll be create a random and try to find this one. It takes time. It's very difficult to solve this one, but it's the best way to solve. Yeah. You have in neural networks you have a call. Every call is learning rate, optimizer, loss functions. They call hyperparameters, and there is a whole field studying just how to set up best hyperparameters for the model. This is one of the most difficult areas. You have to try. It's try and error.
Yeah. So and then we want to minimize our loss function. So in that way, we want to find this.
Yeah, and how do we choose different starting points in the code?
It's random.
Random.
You don't know because you don't know where is the local minima.
Okay, I mean but in the code it seems that we start just from one starting point.
No, yeah, you're gonna create initialize randomly, right?
Okay.
The item optimizer finds the local variable.
What?
The optimizer finds bottom of one of those dips.
Yeah.
Yes.
But if you want to try again, you have to start over.
Yes. Later when we run, we can see we set a random seed here, so you can just try different random seed, I guess. Or there will be other algorithms that will try several, give the random starting point, several random starting point, and take the result, the best result.
Random seed is used to initialize the weights.
Oh. Yes. So I think that depends on the optimizer itself, right?
No, it's up a little bit up. Yeah. When you create this logically, when you're creating these logics, you're not sure, but probably they have this is contribute layers. It's automatically construct these layers. Okay, that inside this line in logics, you have how to initialize the variables, and they have a default value. Okay. So they are just a normal distribution. You can change this one too, and you are not showing here, but it is in that layer, in full connection layer. you are creating a shift tab twice. Right. 8 initialization functions. Here in the second line, 8 initializer.
Oh, this one. 8
Yeah.
Weights.
Weights initializer. Yeah. You're not showing this one. He's taking the full value, and the full value is a random normal distribution with mean 0 and standard deviations 1.
Okay.
You're not showing how to initialize, but in this layer you are initializing randomly the weights. You can change this one.
Yeah, so means we can give an argument to this.
Yeah, you can put the variable there and put another variable. You can create a
fixed point.
Yeah, the standard is normal distributions. Okay, and what you are using now, your people is a truncated normal distribution. So you take a normal distribution and cut off 2 standard deviations. So you just pick the truncated normal distribution. Just pick the 95 confidence levels, and you can set the mean and the standard deviation of this distribution. You can set in everyone, right? So that's why you're not initializing the weights in your code, because you are setting the full value.
Okay.
So that means every time we run this model, we get a different result, because every time we start from a random pick starting point.
Yes, perfect, exactly. So it's possible if you're doing the same model, if you run the same results with now, pick the code with Yan, I run my computer, you are running yours, Yan in here, and you have 3 different results. Pretty similar, but random, you can have a random there, and you change have a different results.
And one more question. So in this model, we just have 2 layers, one input layer and an output layer. So we don't have.
You don't have you don't have a high layer.
Okay, so here the correct prediction is what we use our model, previously defined model, to give the predictor label on our data. This is a function to label our data. And so the accuracy define an accuracy metric. What does this mean? Accuracy equals to dot reduce mean. So we're going to cast. So to correct this function here is to use our label data, and so basically it's compare our to use the label function here and compare to the true value of the label, and to see the accuracy. And if you print, and remember in TensorFlow when you assign all this stuff, all these functions, it's not performed. So right now they are just storing all these functions. Meaning, if you click run, I'll run this. I'll store this as a function, but it's not run yet. So if you print that, it will all they will give you, say, for the image flat. So the flatten process here, it's something like this. So it's a tensor, and if you're going to run that, it will show the result. So like we talked before, how do we run that is use, so we first set a random seed here, like Kevin said, it's used for the weight. And so we give the TensorFlow a random seed, and then sense equals to tf.session, sense.run, and we want a tf global variables initializer, and I think this is a initializer that give you some default values, right? Initialized values.
Yeah. You are when you set global variable initializer, you are cleaning the memory. Any model you have in memory, you are cleaning this memory, and start anew and initialize random variables, the weights, the bias. You are start it's like this is your startup. You're starting your model.
All right.
Okay.
Then we use. Let me run the previous one. Then we yes, it's fine. So sets equals to tf.setting and sets.run this initializer, and for I in range 201, the reason we put 201 here is because I have training data of 1, 201. I need to refer back to the documentation. But what basically it does here is we want to use sets.run with our training operation and loss, and we are going to fit the dictionary of we are going to fit this the following. So X is the images transferred and Y is our labels.
I believe in your print you should print loss value, right?
What?
The last line, the print. The
one?
variable you're trying to is not loss, it's loss underline value.
This one?
Yeah, underline value. That's why you get you don't have value.
No, it's this one. So I.
Where is the second one? Yeah, it's working.
Why it's 201?
It's running.
201, the number of epochs.
You don't have batches, right? Yeah, you run 201 times
Okay.
the model.
Yeah.
Every time you run the model, okay. See dig image trans. Okay, yeah. You run your model 201 times. You run 200 times.
201 times.
Yeah, 200 times you run your model. And for each time it run, it calculates the loss, update the weights, and you see the loss, the error, is decreasing. You are just print it every 10 times it run, you print the loss. That's why you are doing that.
Yeah.
So you see after you run, you print 10 times, you see in the loss in the bottom, your weight is very low.
Yeah, that's because you maybe you go through all your samples and you only made it this far down.
Yeah.
Yeah.
So you
Oh, I
go through all the samples again. You made it this
So
far
I tell the model to run again.
and it
Yeah.
starts from here instead of
Yes.
from here. So you run it again, it gets
Yeah.
down to here.
Oh, I see.
Yeah.
I'll show you why running it too many times is bad though, because you can overfit the model,
Okay.
and it won't be bad at predicting new data.
And then what we do here is we're going to generate some we're going to generate 10 random, select 10 random samples from our training data set, not our testing yet, in our training data set. And we are going to give them label and see if our label is the same as our predicted label is same as their true label.
Looks pretty close. 78, huh?
So if we run here, so you see we have blue means prediction is right. No, green means prediction is right. Red means it's wrong. So if you see here, we see a lot of blue, but this is our training data set, not our testing yet.
And you're testing on the training set. So
yeah.
Same
So then
model.
we want to go to the evaluation part. So the evaluation part, first I'm going to load all the testing data and then do the same thing, transfer the testing data to 28 by 28, transfer it to gray, and then what we use here is to use the model we built from our training data set and use that to predict our testing data set. And we are going to we're going to calculate the match count. So basically and finally output an accuracy number. So the accuracy number is what percent we accurately predict the label. So if we run here, it will give us an answer accuracy of 77.3% accuracy. So that means in our model did 77.3% accuracy in our testing data set. And once you finish, you use sets.close to close all this neural network stuff, TensorFlow. So to just and I also identified a useful stuff called TensorBoard. So what TensorBoard does is, let me show you if I can. What TensorBoard does is it will give you this visualization stuff for your models. So this is basically the code I run so in the Jupyter notebook. The only difference is this is the same code we are using in the Jupyter notebook. The only difference here is here we are having this specified code here. So this code will tell the TensorFlow to write my output model to save it. Then you can later you don't need to go into the training session again to get the model. So write it in a folder as an output, and we can use the TensorBoard to visualize that. So let's run the whole thing here.
That line of code.
Yeah, I'm going to
later though. Oh, 100%.
Okay, so once we finish writing here, we can use log direction equals to, for me, I store all the data in my output folder here. So I specify my log directory output to tell the TensorBoard to read data from the output. And what it will do is it's going to give you a local website. I need to close one. Like you said, it's a live demo, so okay, here. So desktop. So this output TensorBoard Plus. So here we can visualize our result. And when you write, when you are defining your layers, and when you're defining your functions, you can add a name to that. So then it will make more sense here. Otherwise, you see it just give you the name what we give the function name. And actually, in that function name, you can tell it to write a name for the one you want to see. So it will give you more like a graph that makes more meaning. And also, this TensorBoard also have a function that when you are running a neural network, so every time you have you get these losses here, so you can also store this output in this output in a file and use this TensorFlow to visualize your loss, the trend of your loss function, and to visualize your result. Okay. So basically that's it. I did 1/4 of the presentation, and Mauricio did 3/4 of it.
So where did you get the tutorial to do this?
Oh,
DataCamp.
DataCamp?
this is DataCamp for the TensorFlow, but the TensorBoard is not included here. TensorBoard, I did. TensorBoard, well, you know, like you told me, the best way to find an answer to a question.
Google it.
Google it.
The TensorFlow website is very good. It's very good. There is a plenty of samples and codes you just copy and paste. You can run by yourself. It's very good way of source. DataCamp is very good too. I really like this one.
Okay. Well, thanks.
So actually what we didn't do is change the sigmoid function, right? So we have, what I use is soft plus, and we can change to sigmoid, and I can tell you when I change to sigmoid, the accuracy rate is 1%.
1%.
1%.
1%. If you use ReLU, it's like 50 or 60%. But if you use sigmoid, it gives me an accuracy rate of 1%. So, but with this code, what definitely you can do is to change the function to see the result, how the result change, and also change the learning rate, the optimizer method, and everything.
Cool.